Okay, good afternoon, everyone. Welcome to the CERN colloquium. It's a bit unusual time today, Wednesday, but the usual time of the day. We are very pleased and very happy to have a very distinguished speaker today, Professor David Gross. I would like to shortly introduce him, even though you probably all know him. So David Gross is a Chancellor's Chair Professor of Theoretical Physics and the former director of the Kavli Institute of Theoretical Physics in Santa Barbara. He received his PhD in 1966 from Berkeley. Before joining KITP, he was a professor of physics at Princeton University. He was awarded the Nobel Prize in Physics in 2004 for the discovery of asymptotic freedom and the theory of strong interactions, and on the way he received many other prizes. But this year it has been 15 years since the discovery of QCD, and it's a great honor to have this story being told by the inventor of the theory. So thank you very much, David. We're looking forward to your talk.
Thank you, Sasha. So it really is great to be back at CERN in this room where I've given many lectures and celebrating 50 years. That's wrong. Sorry. 51 years of QCD. So I've given this talk a lot, and some of you, I know have heard it, over the last year, a year of celebrations. What can I say? We're now here, we're celebrating 70 years of CERN, which is really remarkable. I was not here in 1954, but I was here for the first time in 1968-9 for half a year. It was one of the most productive years of my career. It was wonderful, and I've been back many times. So, we tend to celebrate anniversaries that end in 0, 50 years, 70 years. We're nearing the 100th anniversary of quantum mechanics, which reshaped our understanding of physics about 100 years ago, approximately. That should be a lot of fun in the next few years. But I'm going to start my story way back at the beginning of nuclear physics, the beginning, in a sense, of particle physics, with Rutherford's experiment that revealed the structure of the atom and discovered the nucleus, and invented the way we do experimental particle physics, and same method we still use today. 3 Nobel Prizes he should have gotten in physics, not just chemistry, but he died too early. So Rutherford, in order to try to understand what was going on inside the atom, which nobody knew, they knew there were electrons somehow. The electrons had been extracted, identified, measured by Thomson, but what was going on inside? And Rutherford sort of, I think, really invented the method we use today. To see what was going on inside the atom, he smashed nuclei, alpha particles, that he had made his early career on gold atoms, as you know, to see what was going on inside the atom. And his detector was rather primitive. It was a scintillating screen, and his students, an undergraduate student and a postdoc, Hans Geiger, I forget the name of the undergraduate, what? Marston, right. Left physics, however. They in a dark room, they sat for hours so their eyes would be sensitive and measured the scintillations on the screen. And Rutherford used electromagnetic theory to study the deflection of the charged alpha particles off atoms. And of course, what he discovered was that many of the alpha particles came back or were deflected at large angles, and in fact fit the Rutherford cross-section given by E&M if the atom was mostly empty and had a very small nucleus at its center, where all of the positive electric charge resided in most of the mass. So Rutherford discovered, therefore, the structure of the atom and immediately suggested a kind of planetary model for the atom. That planetary model classically is unstable, and that led Bohr within 2 years to suggest the Bohr model, and theorists trying to understand, make sense of the Bohr model and apply it to other atoms were led within 10 years or so to quantum mechanics. But in addition to the structure of the atom, Rutherford also discovered the nucleus of atoms, which is the subject of today's talk and of what we've been doing in particle physics ever since, trying to understand what goes on at the subnuclear scale. So 3 great discoveries: the nucleus, the atom, and the experimental method for probing short distances, inventing experimental particle physics, if you want. Well, now I'll switch. Of course, these are our modern Rutherford experiments and our modern accelerating beams and our modern detectors, but it's really conceptually the same idea. So I started graduate school at Berkeley at a time where Berkeley was one of the centers of experimental particle physics. New particles were being discovered all the time at the Bevatron, 1,000 times less energy than the LHC. And that was, of course, not the center of mass. But it was a very exciting place. New hadrons were being discovered every week. It was really exciting. And what attracted me was the nuclear force. Of course, by then we knew that within the nucleus there were 2 forces acting, the weak force, the strong force. But the nuclear force was especially mysterious. And why was it so intractable? Well, first of all, it wasn't at all clear from the beginning which were the elementary particles. More and more were added as they were discovered. Started with the proton. It took 20 years to discover the neutron. And then the pion, suggested by Yukawa as the quanta of the field that held nucleons together, and then strange mesons and strange particles, and so on and so on. There were just too many elementary particles, which all seemed to be similar. Second, there was no obvious principle to determine the dynamics at all. And finally, it was clear that the interaction between these particles was very strong. The pion-nucleon coupling was not small. In fact, it was quite big. How could you possibly calculate, since theorists only knew how to do perturbation theory at that time? Now, after the great success of quantum electrodynamics, people tried to construct meson theories of nuclear forces and failed. Dyson tried very hard, and after a few years gave up and essentially left elementary particle physics and said, 1960, the correct theory will not be found in the next 100 years. It's very typical of theorists. If they can't solve a problem, it's not going to be solved for 100 years. But he was off by, of course, 87 years. The general feeling was that a revolution was needed. This was such a weird, so different than atomic physics, where the constituents, the electron and then the nucleus, were evident, and the forces were just given by Maxwell. One just needed to quantize the electromagnetic field. Here, presumably, a revolution was needed. Now, of course, we know now the reason it was so hard to make progress early on was that the charges, the sources of the fields that transmit the forces, the colored quarks and gluons are completely hidden, confined inside colorless hadrons. And that's a totally new phenomena that had not been encountered before, wasn't even dreamed of. And as hard as you smashed protons, produced lots of new hadrons, but no quarks. Now, quarks had been invented. As one produced new hadrons, there were new approximate symmetries and patterns of the masses and the quantum numbers of hadrons, and quarks were invented to systemize those patterns, but clearly they weren't real physical objects. You couldn't produce them. They were nice mathematical objects. And then quantum field theory, which was the basis,
Yes. This is what I asked previously. Yeah, don't worry.
No, I thought you were on Skype, but maybe
Somebody
Sorry?
talking.
I hear it's David Gross.
Yes.
I don't think you are talking with David Gross, right?
No. There is a colloquium conference with him.
Is that a comment, a question, or? Anyway, so the theoretical framework that was available at the time had been so successful for QED, quantum field theory, was under severe attack. Renormalization, which had dealt with the problems of QED, was thought by its inventors to be a trick. They didn't really understand what it meant until Wilson, really. And it was thought to be a trick. It was sweeping infinities under the rug, and it was a sign something was wrong with the theory. There were also no non-perturbative methods. So I took my first course in quantum field theory from Steven Weinberg, who was a professor at Berkeley. And the first walks into the class, says, "This is a course in quantum field theory," writes on the blackboard, "Quantum field theory equals Feynman diagrams." That was the attitude at the time. Path integrals? Nobody had heard of path integrals. Nope. There was a theory, a quantum field theory, today we would say an effective field theory, of the weak interactions. Fermi's four fermion theory, current-current interaction, very successful effective field theory. But it was clearly a low-energy approximation. Cross-sections blew up at high energies. It was non-renormalizable. But at low energies, it was weak. You could treat it perturbatively as an effective field theory, summarize the data. It was fine. But the strong interactions couldn't do that. Yang-Mills theory, of course, had been put forward as a not-abelian generalization of the gauge symmetry that underlies electromagnetism in 1954. But it had massless gauge bosons, massless photons, and clearly in conflict with reality. People tried immediately to apply it to the strong interactions, coupling it to flavor, the only known symmetry of the strong interactions. Isotopic spin symmetry, SU3 flavor. Today we realize those are accidental symmetries, which are simply there because the light quarks are light compared to the QCD mass scale, and they're not exact. And of course, it's nonsense to gauge a non-exact symmetry. So that went nowhere. And there was a more conceptual, fundamental attack on quantum field theory. So my thesis advisor, Jeffrey Chu, led that attack from the west coast of the United States. There were two ideas. One, all these hadrons that were being produced, they all look equally fundamental. So instead of saying that matter is made out of point-like constituents, atoms, or he said all hadrons are equally fundamental. You could understand some of them as bound states of the others, but vice versa. But then how do you construct a theory? You don't have fundamental particles, write down some kind of Lagrangian that couples the fundamental particles. Instead, and quantum fields in any case are unphysical. Who ever measured a quantum field? So his idea was that general principles such as conservation of probability, unitarity, or causality, which leads in relativistic quantum field theory to the principle analyticity of the scattering amplitudes, which is what one observes. The idea would be that you would demand that the S matrix, what you observe, satisfies those general principles. And since at that time one had never heard or constructed a completely relativistic scattering amplitude which satisfied those general principles, maybe general principles determine a unique solution. That's a very radical idea and remarkably very appealing. Certainly appealed to me as a student, and it took me almost a year or two to get dissatisfied with it. Remarkably, it's reappeared. A whole generation, some of who are in this room, who find it very appealing. There was another attack on quantum field theory on the opposite side of the world, in the Soviet Union, where Landau, a great physicist, reigned supreme. And he and his colleagues studied renormalization of the charges, especially in quantum electrodynamics, and discovered a phenomena which was called in Russia the problem of zero charge, or the Landau pole. This is a real phenomena. The spirit of the times was they did a calculation, what is in some sense lowest order perturbation theory, and on the basis of that concluded that in all theories, the physical coupling that you measure, the fine structure constant, quantum field theory, to define the theory, you need to introduce some kind of ultraviolet cutoff, it would appear, and that defines the Baire coupling. If you want the coupling at arbitrarily short distances, where in a local theory the couplings are defined, and then you calculate the Baire coupling you measure in your laboratories at macroscopic distances. And they found that the physical coupling is a function of the Baire coupling and the cutoff, lambda, and vanishes for any value, no matter how you make the Baire coupling big, as lambda goes to infinity. That's the problem of zero charge. You try to define the theory, you want to have a finite electric charge, but no matter how big you make the electric charge at short distances, it vanishes macroscopically. This is simply the phenomenon of screening. The vacuum in relativistic quantum mechanics is a medium containing virtual electron-positron pairs, dipoles, which obviously screen a charge that you put into the vacuum. And in QED, that screening is very powerful, so powerful, it of course screens the charge, so as you go out, the charge you seek is smaller, but it's so powerful that it completely screens any charge you put in. So at large distances, the charge vanishes. That's the zero charge problem. Dielectric screening. The conclusion they drew, Landau was a very bold physicist, was, first of all, this was true for all theories. They looked at a bunch of theories, same kind of screening happened, and he reached the conclusion, 1960, that within the limits of formal electrodynamics, which really means quantum field theory, a point interaction, local interaction, is equivalent no matter how strong you make the coupling for any intensity, whatever, to no interaction at all. So he was driven to the conclusion that the Hamiltonian method, or quantum field theory, for the strong interaction is dead and must be buried, although with deserved honor. Now, notice he says the strong interaction. That's because he understood that this problem occurs also for QED. That's where it was discovered. But for QED, you have to go out, you have to make this cutoff very big for it to be a problem, because the coupling starts out very small, but not for the strong interaction. Conclusion was that if the same phenomenon occurs for the nuclear force, for strong interaction, the problem immediately at a few GeV, you'd run into serious problems. Now, must be buried, Landau was very powerful. And when he said must be buried, it meant that his students and his postdocs were not allowed to work on quantum field theory. And my friends Polikov, Migdal, who continued to work on quantum field theory, had to argue that they were really doing condensed matter physics. And Landau had strong lieutenants who enforced this rule very strongly. So this was a different attitude, but the same conclusion. Quantum field theory is not the answer. What was happening experimentally? Well, there, instead of the theoretical impotence that was prevalent, there was experimental supremacy. It's enormous experimental excitement. Discoveries, new particles were being discovered every month, new patterns, wonderful, just the opposite of today. But there are some lessons to be drawn as well. Many theorists and experimenters believe that the secret of the strong interactions lay in the high energy behavior of scattering amplitudes for low momentum transfer, for diffraction scattering, for the total cross-section. Every time a new accelerator was built, the first thing that was done was to measure the total proton-proton cross-section. Nowadays, I gather it's hard to get people to agree to do that experiment here at CERN. Nobody cares. But that was the central experimental issue back then. Diffraction scattering. Now, why was this? Well, I think the real reason was experimenters like to work in regimes where there's a lot of events, a lot of data, a lot of good statistics. And most of the events are in scattering of particles in the forward direction. So it was experimentally easy. New patterns were discovered. Reggie behavior, shrinking of the diffraction peak. Theorists were discovering new ways of thinking about diffraction scattering, Reggie theory, Reggie poles. And the two reinforced each other. The theorists told the experimenters, that's what's really interesting, measured diffraction scattering. The experimenters said, great, that's where the statistics are best. No one was particularly interested in high momentum transfer, where the secret of the strong interactions was indeed to be found. So this is an important lesson. One can get into these loops where theoretical prejudice and experimental ease coincide and other directions are neglected. Well, so personally, being disappointed with the bootstrap, where one had these some rules where you had two sides of bootstrap relations, and you showed that, they were sort of satisfied. You didn't really learn anything, except, of course, that the general principles you started with weren't being violated. Okay. So I got totally fed up with that and moved from the West Coast to the East Coast, where field theory was tolerated, and started learning about local fields, local currents. And with Callan and others, derived all sorts of sum rules for a new experiment that was going to take place at SLAC, deep inelastic scattering, where one could measure matrix elements of local currents. Now, again, the theoretical situation at that time was exactly the opposite of today. Theorists could get away with anything because there was no real theory. So any kind of stupid approximation you made, or brilliant approximation you made, was tolerated as long as you could make a prediction. And in those days, you could make a prediction and it would be tested within a year or two, or a few months, not 50 years. So that was a great time. And these sum rules, which were derived by what we would say today was, lowest order perturbation theory, or just free field behavior of the operator product of local fields, led to all sorts of interesting predictions, which were really not justifiable, but could be tested. And some of them using the so-called quark model, which was really just saying the currents, the electromagnetic current of hadrons was that of free quarks, led to various predictions, which could be tested in this experiment at SLAC. Now, the deep inelastic scattering experiment at SLAC, started in 1967, I believe, was a redo of Rutherford. This was exactly the Rutherford experiment. One wanted to understand what was going on inside the proton now. So one scattered electrons, which are point-like particles, off the proton, producing high virtual momentum photons, which could see to very short distances, in effect, inside the proton. This was not the experiment that everyone at SLAC wanted to do. The people who did made an incredible discovery, which we now was understood later to indicate that the proton looked as if it was made out of freely moving quarks when viewed in these experiments at very short distances and short time intervals. They found the phenomenon of scaling, which is a property, clearly a property of free particles, and the quark model sum rules and indicated that, well, these particles kind of looked like they were quarks. They had spin 1/2, they had fractional charges, fractional baryon number, if you believed in these sum rules. This experiment, of course, was awarded the Nobel Prize for the experimental discovery of quarks. But, okay, it was an amazing discovery of, by the way, again, the data. It's really interesting, today's world, to go back and look at that original data. This was very low energy. The data was really crummy. They actually had to use our sum rule for the spin in order to improve the statistics, which was at best at the level of 20, 30%. But if you extrapolate, you had faith, you could say that they saw this free point-like behavior. And certainly well, a lot of confusion after the discovery of scaling and point-like structure within the proton. But, I'd worked on this, my sum rules worked, so I was kind of convinced that hadrons were made out of point-like particles, constituents. And furthermore, they looked like quarks. Quarks somehow were real. You could see them moving over short distances and short times within the proton in these experiments. But of course, quarks had to interact very strongly, otherwise you'd produce them. And once you turn on interactions, these free fields like sum rules and scaling broke down. So this, was, for me, was an obsession for the next 5 years or so. Now, I had a slight detour into string theory. Actually, that occurred while I was here at CERN in 1968-9, where I worked on sum rules with Llewellyn-Smith, for example, but also on the Veneziano amplitude and the dual resonance theory. Very exciting time, very different approaches, and but strings are very soft. See, the behaviors seen at SLAC indicated point-like constituents, which interacted very simply and gave power law fall-off at large momentum. Strings are very soft, and when they scatter at large momentum transfer, cross-sections fall off exponentially. Just a characteristic of these soft, extended objects. So I gave up on string theory completely and went, because they could not explain scaling. By 1972, I had a plan. I was going to make my advisor, Geoffrey Chew, happy by destroying quantum field theory once and for all. The idea was to take the experiment seriously. Scaling is, which for the experimental evidence was getting better and better, was an experimental fact, and that would require asymptotic freedom, which means that unlike QED, the coupling in whatever quantum field theory could describe, deep inelastic scattering would get weaker at short distances, what we called later asymptotic freedom. And that actually one could almost prove, and Callan and I, generalizing some work of Giorgio Parisi, proved that for all theories except Yang-Mills theory. In fact, it's not, well. The other part of the argument was to prove that there are no asymptotically free theories. And that was the expectation, certainly of Landau. Charge screening, charge renormalization, is vacuum polarization, is screening of charge. And that should be infinity. The coupling gets stronger at short distances. It's screened at larger distances. And that was sort of proved by Coleman and I, all of this at the end of 1972 and 1973, that there are no asymptotically free theories. That's possible to prove such a very strong statement, because if a theory is asymptotically free, it means that that the couplings get arbitrarily small at short distances. And therefore, one can study short distance behavior perturbatively. And we know how to do perturbation theory for all renormalizable theories, any number of fields, except Yang-Mills theory that wasn't provable by our methods. And so we proved that there were no asymptotically free theories. So the idea was, if you believe in scaling, can't explain it by quantum field theory. The one theory that we couldn't deal with was Yang-Mills theory, and this is where my first graduate student, Frank Wilczek, whom you see here, when he still had hair, a beard. And we worked together to fix this final hole and discovered that non-abelian gauge theories, Yang-Mills theories, had the remarkable property of unique among renormalizable theories of asymptotic freedom. And therefore, okay, that is required by experiment. This is the only theory that has such a property, so one should look for a non-abelian gauge theory of the strong interactions to explain Bjerre-Kane scaling. For me, it was indeed a big surprise. This one theory, which had come back into vogue in the early 70s, of course, with the resurgence of the electroweak theory of Weinberg, Salam, and Glashow. And once you accepted that argument, then the theory, given what we knew about the strong interactions, was forced on you. You had no choice. The dynamics had to be that of a non-abelian engaged theory, the force mediated by gluons, the rank of the group had to be 3. We'd already had much evidence that in the thinking of hadrons made out of quarks, quarks had to have 3 extra labels. Colors, we call them, red, white, and blue, red, green, and blue. So it was absolutely clear the only possible theory that was asymptotically free, based on quarks and what we knew experimentally, had to be based on an SU3 color gauge group. 3 triplets, 3 flavors, which were known at the time. That's QCD. Now, why is QCD asymptotically free? Why is it not screening but anti-screening? Well, it's simply best understood in terms of a magnetic picture. In a gauge theory, you can think electrically or by a dual transformation magnetically. So if you consider the vacuum in QCD, there are, of course, virtual quark-anti-quark pairs, but there are also virtual gluons. And gluons are charged. Non-abelian gauge theory, the carriers of the force themselves are charged. Gluons carry red anti-blue charge. There are 8 charges. Gluons have a spin. They're charged spinning particles. So they have a magnetic moment. So you can think of this as a magnetic medium with permanent magnetic moments. And then you have the phenomena of paramagnetism. You put an external magnetic moment into the QCD vacuum, the gluons will align, increasing the charge at long distances and thereby decreasing it at short distances. This is paramagnetism. I've always wondered why Landau, who is an expert on the phases of quantum theories and condensed matter physics, didn't think of his problem as being diamagnetism or dielectric medium, and think of trying to look for a cure by a paramagnetic medium, which does require not permanent magnetic moments. Now, in the larger paper, we started making predictions. The great thing about QCD asymptotic freedom was that it said that at high energy or short distances, the couplings become weak. You can then do perturbation theory and make predictions about deep inelastic scattering, the logarithmic violations that are predicted, but also started to address the question, what happens at large distances? How come you can't take the quarks out of the nucleus? The vogue then with thinking about Yang-Mills theories and electroweak theory was the Higgs mechanism. The symmetry, you don't see the symmetry in massless gauge bosons because of the Higgs mechanism. Symmetry is spontaneously broken. But it wasn't going to work for the strong interactions. So one could imagine that symmetry is not broken, which would appear to be ridiculous because then you'd have this problem of strongly coupled vector bosons and massless. But in asymptotically free theories, we realized that that naive expectation could be wrong because at large distances, the coupling becomes stronger and stronger. And there may be little connection between the free theory and the spectrum of states. Interactions don't just change the masses and the couplings, they could completely confine the charged particles. Now, that was a conjecture, of course, still is to some extent, although the evidence for confinement, permanent confinement of quarks inside hadrons is extraordinary. From lattice QCD, from experiment, no one has ever produced a quark, even at the LHC, so on and so on. Now, well, how do we believe that happens? Well, the strong force is mediated by gluons, by the chromodynamic field, much like the electromagnetic force, but in this strange medium of fluctuating gluon-charged, colorly charged fields, the medium is paramagnetic, and that squeezes these flux lines, electrical flux lines, into a tube, we believe, of area that doesn't grow as you pull the quarks apart. And then that leads to confinement. Just Gauss's law tells you that the electric field of these flux lines does not fall off with distance. Like in Coulomb's law, remains constant, and the energy it takes to separate two quarks increases linearly with distance. You cannot pull quarks out of the confined hadrons. And this, of course, is a lattice QCD simulation of pulling two massive quarks apart in the QCD vacuum, and you see the flux lines confined to this fat flux tube or kind of fat string. The connection with strings is, of course, very interesting. Now, of course, what happens in reality, if you have dynamical quarks, eventually you pull a quark pair out of the quark-antiquark pair out of the vacuum, and this meson splits into two mesons. That's what happens at the LHC. If you take a quark, you smash protons together, you produce these quarks, they pull pairs of quark-antiquarks out of the vacuum, and you get a spray in the end of confined hadrons. Now, it was interesting, very interesting, to follow the impact this discovery had on the community. The acceptance of QCD for a small group of theorists, whom I call the smart crowd, was almost immediate. Oh my God, this could explain everything. Everything we knew, more or less, about the strong interactions fitted into QCD. There were a few puzzles. They got resolved rather quickly, but everything fit in, and you could start doing calculations. And it was really interesting. Then there were people who simply were of the next generation to these people, who just couldn't adjust to new ideas. And then there were people, very young people, but didn't know any field theory, had no idea what this was. And it took them quite a while to catch up. But this is a list of people who reacted immediately and started contributing. Among the rest of the community, there was slow growth. Now, there were immediate calculations. I said you could calculate because couplings are small. There's nothing theorists like better to do than to calculate, especially in those days where you could make predictions that could be tested. Now, in the case of QCD, it took a long time because the effects are logarithmic, but still you could calculate. And there were a lot of very interesting calculations that were done almost immediately. There were also theoretical milestones, which for me were very important. Perhaps the most important was Wilson's invention of lattice gauge theory, which provided a framework where you could solve QCD as a multidimensional integral with by introducing a space-time lattice, and then try to take the continuum limit. But before you took the continuum limit at strong coupling, confinement was obvious, and the issue was then, could you push this strong coupling calculation down to zero coupling? As the lattice spacing, as the distance goes to zero, the coupling should vanish, asymptotic freedom. Then there was, well, we developed cases where dimensional transmutation, which I'll come to in a moment, happens, and it Hooft solved large N QCD, large number of colors. It could be solved analytically in 2 dimensions, where confinement is kind of easy, but still you could construct a theory of elementary particles that could never be seen experimentally, of confined elementary particles. I used to have big arguments at Princeton with Eugene Wigner, who famously defined what an elementary particle is. An elementary particle is something you observe far away, not interacting with anything else, characterized by its mass and its spin, a unitary representation of the Poincare group. The idea that you could base a theory on elementary particles that you could never see seemed to him total nonsense. But here was an example. The interesting turning point for many physicists was electron-positron annihilation. Now, electron-positron annihilation, as you know, is a great way of measuring the charges of the elementary constituents of matter. And this is a plot of what was known roughly in 1974 of E plus E, the ratio R of E plus E minus annihilation into hadrons compared to electrons. So it measures the sum of the squares of the elementary charges of the constituents. And QCD would predict a straight line. That red line agreed with experiment with 3 colors and 3 flavors. Then in 1974, I was at a meeting in Trieste. I gave a talk on QCD, all the reasons that it had to be the theory. And then Bert Richter got up and said, yeah, but look what we've now measured. See these last few points, the new collider at SLAC? Cross-section isn't constant. It's rising linearly. And with great enjoyment, he said, QCD is dead, scaling is dead. Now, some of the theorists in the audience knew very well that there had to be other quarks. The electroweak theory required charm quarks. But theorists were very timid at that point in time. After all, they'd been totally unsuccessful for so many years. They very timid. But indeed, as you know, Bert went back to SLAC and soon discovered charm quarks. And this rise in the cross-section wasn't a breakdown of scaling or of QCD, but rather the opening of the charm threshold. And of course, the history of comparing QCD with scale experiment or E plus E minus annihilation is a great story. Much of it occurred here at LEP. So what about asymptotic freedom? Well, this is 16 years after discovery of asymptotic freedom, Guido Altarelli reviewed the subject and said, okay, it's really been tested to about 1%, no, 5% accuracy. Yeah, but so those are a bunch of experiments. Those black lines are theoretical uncertainty. It sort of fits, but so does a straight line. It really took a long time to test quantitatively with precision QCD because the effects are logarithmic. This decrease is logarithmic. This is a situation 40 years after. It's now pretty good, very good, and of course, many other precision tests that go into measuring alpha S. This is a precision of world compilation of many, many different experiments we're getting. And this, by the way, is a very recent result from Atlas that was given to me yesterday. Preliminary, quite remarkable. This is one experiment in jet production, and it's the lowest data point there. That's one experiment with a precision now of 0.5%. And, by the way, exactly equal to the calculation of lattice QCD, where you can calculate alpha S at the Z mass, or actually at the mass of the hadron, presumably the proton, which is well measured, defines a scale, and then the coupling in QCD is calculable with the same precision, actually a little better as the Atlas measurement. And of course, the world average is in agreement as well. So now we have precision tests of the theory, but it took a long time. The original deviations from scaling that we calculated took a long time to detect. We now have, as you know, dozens of very high precision measurements. And theory has learned how to control the vacuum using lattice gauge theory and calculate the masses of hadrons, in addition to other calculations. And lattice QCD really remains so far, our only tool for this level of precision in hadronic physics. But it now competes with these incredibly precise LHC experiments. So this is a plot of the light hadron mass spectrum as calculated by lattice gauge theory, which is now, again, at the better than 1% level, including, remarkably, the neutron-proton mass difference, which is due to the differences of the up and down quark masses, electromagnetism, and QCD. This is amazing for a theorist. This was started 40 years ago in earnest. It took 40 years to get to this precision. It required an increase in power, theoretical calculational power, by 18 orders of magnitude. Now, 9 of them were provided by Moore's law, the increase in the power of computers. But 9 orders of magnitude, a factor of 1 billion, is estimated to come from better understanding of QCD, finite size effects, chiral symmetry breaking, better algorithms, improved techniques. So 1 billion from computers, 1 billion from theory. A factor of 10 to the 18 was required to achieve this level of precision. But now we have this tool. And as you know, it's extraordinarily useful for rare decays and other things as well. And in the future, one hopes for much more quantitative control of QCD. In the future, well, theory also does, has learned how to generalize our simple perturbative calculations of 50 years ago to incredible accuracy, calculate backgrounds to experiments one carries out here, not just the leading order, which we started, but next to leading order, and next to leading order, next to next, and next to leading order. And that, too, required not just a lot of work, but the discovery of incredible new structure within scattering amplitudes, which has many other implications. I just want to end by discussing, boasting about QCD as a perfect theory, in a sense. By perfect theory, I mean it has really no infinities. It has no adjustable parameters and no new physics. Okay, no UV infinities. So this problem that Landau talked about, to get a sensible theory, the bare coupling between particles at arbitrarily short distances had to blow up. You had to introduce a cutoff to deal with that, and that didn't help either. Doesn't happen in QCD. The bare coupling vanishes. You never get infinities in your calculations if you do it the right way. For example, lattice QCD, where you write down the solution on a finite lattice, you introduce a coupling that characterizes the gauge theory at short distances of order of the lattice space. And then you take a limit, and the theory tells you how to take the limit. That's asymptotic freedom. And if you do that, you get a finite answer. You should, and you do, and you never have to sweep infinities under the rug. They never appear. Second of all, the theory has no adjustable parameters. Now, recently I went back and looked at Feynman's summary of the situation of quantum electrodynamics in 1961 after 10 years of great success. And, but at the end of his talk, the Solvay Conference 1961, he tries to ask, could QED be a complete theory? What he wanted to do was, QED has two parameters, the fine structure constant, 1 over 137, the mass of the electron. Well, assume the electron had zero mass. We get rid of one parameter. Could that mass somehow be calculable? He understood that chiral symmetry breaking could occur, so that problem wouldn't be a problem. But he did also think that that would be impossible, because the system, if you turn off the electron mass, is scale invariant. So how are you going to generate a scale if the theory has no scale? And so he said, Feynman was always careful, I'm not certain, but it appears to me impossible to generate a specific length from no scale at all. I remember here at CERN, 1974, when I visited after QCD, and had, big arguments with John Bell. Bell was a very interesting character because he was always, somehow he always got to the bottom of things that were conceptually difficult to understand, and he was just couldn't understand the fact that you could generate in a quantum field theory a scale if there was no scale to begin with. But that's what happens in QCD. It's called dimensional transmutation. In the case of QED, Feynman concluded QED is incomplete. Of course, you couldn't calculate everything. Couldn't calculate the electron mass or alpha. Quantum effects, however, break scale invariance. That's the screening renormalization. It's a real physical effect. The world is not scale invariant, even in a classically scale invariant theory, because the vacuum is complicated and looks different at different scales. So QCD has no real adjustable parameters because of that. Unlike QED, everything is calculable. Now, what do I mean by that? Well, consider the proton. In QCD, the proton is sort of like a bag. That was a qualitatively model of a proton. Inside this bag, the quarks move around freely. If you make the bag bigger, however, the force between the quarks, the energy it takes to make the bag bigger, pull the quarks apart, gets bigger. So the bag stabilizes. At what length scale? Well, let's call it, once you have the length scale, then the mass of the proton is simply the mass of these confined gluons and quarks within the proton. That produces the mass scale. Okay, let's call that the proton mass. That defines, by the way, what the couplings are at that scale. So I've introduced a scale because I have to carry out measurements. I have to know what to compare to. So in QCD, you produce a proton. Let's call its mass MP. Alpha, the couplings are then determined. That theory tells you how they vary with scale. And then you'll never be able to calculate the proton mass by itself because there isn't any parameter, dimensions of mass in the theory. But you never measure something directly anyway. You only measure it relative to something else. So the strong interaction coupling is calculable, and all mass ratios are calculable. And that's physics. We don't measure masses. We measure masses in units of some convention, which used to be a block of material in Paris. Now I think at some number of carbon atoms or something. So QCD, if you neglect the quark masses, has no adjustable parameters. Also has no new physics. At short distances or high energies, it becomes simpler. Perturbation theory becomes simpler. Extrapolate the theory, nothing happens. It gets better. So we don't expect anything new to happen if we only had QCD. That has very important implications for science. It makes the early universe simple. It enables us to imagine the unification of the forces, and it solves the so-called one of Dirac's large number problems. So, as I remarked yesterday, by the way, when they asked about the applications of the standard model, well, we can't claim, new technology yet, but we have made it possible for astronomers and astrophysicists and cosmologists to understand the early universe before the CMB by extrapolating the standard model. And instead of having a hadron hell, nuclear physics, who knows what's going on, we have quark soup. And one of the things that was realized almost immediately after QCD emerged was that if you heat up hadrons, they're going to melt. Right? At very high energies, high temperatures, or high densities, you get into the region where you can trust perturbation theory. And in perturbation theory, clearly quarks and gluons are not confined. So one expects a phase transition, and that phase transition, if has definite astrophysical implications, but they can be explored within a well-defined theory and experimentally. And the various phases, potential phases of QCD are being explored. They're actually discovered here at LHC 24 years ago, first indication. of a phase transition to a quark-gluon plasma. Finally, the fact that the strong interaction coupling becomes weaker enabled us to extrapolate the standard model forces from where we currently observe back to very, very, very high energies. And when extrapolated over 18 orders of magnitude or so, the forces in the middle 70s seem to converge. Of course, the forces and the quark and lepton spectra, the gauge groups fit together so completely with no missing components that strongly motivated the search for unified theories and remains, in my opinion, the most important clue we have as to the future of fundamental physics. At these very high energies, perhaps below, perhaps at the Planck scale where quantum gravity becomes a strong quantum force, it looks like the forces should be described by some unified theory. Of course, was one of the big motivations for string theory application to unified theories in the middle 80s. Finally, there is this, Dirac had a whole list of small numbers or big numbers. The ratio of the proton mass to the Planck mass is 10 to the minus 19. Very important number. This number explains why gravity is so weak in this room. It explains why we exist. Dirac was not able to imagine calculating such a number. He was wise enough not to invoke anthropic arguments. He could have said, okay, if this number was 10 to the minus 3, we wouldn't be here. Because if this number was 10 to the minus 3 and you put together 1,000 protons, you'd form a black hole. And certainly not 10 to the 23 proton. So, but Dirac was much too clever to invoke anthropic arguments. So what he did instead was relate a bunch of these numbers, like the radius of the universe today, to the size of an atom, and a bunch of such very small, or turn them around, very big numbers. They should all be related, he said, even though I can't calculate any of them. And that made a prediction. So Dirac was really good. And he made a prediction that on cosmological scales, where the radius of the universe changes, some of these numbers which have to do with fundamental constants should also change. So he predicted that cosmological scales, like billions of years, the fine structure constant, Newton's constant, might vary. And that could be tested and has been tested, and it looks like it's largely ruled out. But QCD essentially solves one of these large number problems. The one I just referred to, the ratio of the proton mass to the Planck mass. Now you have to make certain assumptions, obviously. At the Planck mass scale, everyone's unified. All the forces are unified. The couplings are kind of the order of electromagnetic couplings or whatever. We extrapolate from current theory. Then at that scale, Planck mass, that's determined by Newton's constant, Planck's constant, and the velocity of light. The coupling is roughly, like the electromagnetic coupling or the extrapolation of current couplings. What determines the proton mass? Well, we have to go to lower energy. The force between the quarks gets stronger, larger distances. Eventually it becomes strong enough to hold the quarks together. That defines the mass of the proton, and the relation is given by asymptotic freedom. And that is roughly, 10 to the minus 19 plus or minus 1 or 2. Yeah. So this incredibly large number is due to the logarithmic running of the coupling. You have to go to very large distances before the coupling is strong enough to hold the quarks together and define the mass of the proton. So we do understand that large number problem, which has always given me hope that we could understand other large or small, for example, the cosmological constant, or other small numbers that appear in physics and seem so hard to calculate. Okay, so QCD is indeed a perfect theory, no adjustable parameters, no indication of where it breaks down, no infinities, infinite bandwidth. But of course, why are there 3 colors? What about the quark masses and mixing? QCD says nothing about those. And of course, there are other forces in nature, including gravity. So, but it does, give an example of what we should aspire to. And I myself would be very disappointed if we had, say, a unified theory of the forces which wasn't as powerful as QCD. But the remarkable thing, of course, illustrated in those flux tubes, there was the relation between the confined flux tubes of QCD and strings, which has become a pivotal part of our trying to understand fundamental theory, and is really fundamental. String theory was discovered in an attempt to understand the strong interactions because these flux tubes do look like strings. We still are searching and expecting to find some kind of string theory of hadrons, string theory of the strong interactions. It's bound to exist, just hard to construct explicitly. But fundamental string theory has, in addition to these open flux tubes, closed strings, which turned out to describe gravity. And of course, that has led us on a search for a unified theory, including gravity. And now with the modern tools of dualities between string theories and quantum field theory, actually between fundamental string theory and supersymmetric cousins of QCD, supersymmetric gauge theories, we have a hope to be able to analytically solve QCD itself, because some of its cousins are, one, much more simple, higher symmetry. The supersymmetric cousin of QCD is almost soluble. And one could imagine solving, understanding that theory much better, and then deforming it, which can be, in some sense, continuously done to lower supersymmetry or even real QCD, and then include real quarks. And all of this, in principle, could be imagined, one could imagine doing sometime in the future. So what about the future of QCD? Well, there's a lot of work to be done. Electromagnetism has been studied now for more than 150 years, and people continue to work on E&M, which from the point of view of QCD is an utterly trivial theory. Perturbatively, one is discovering an incredibly rich structure of the perturbative expansion of gauge theories. Numerical techniques can go way beyond, one believes, lattice gauge theory, especially with quantum computers, and attack some really hard problems, not the static masses, but diffraction, fragmentation, hadronization. Experiments continue. In the case of QCD, here at LHC, there are 2 experiments that are probing the nature of the quark-gluon plasma, which is a fascinating new form of matter, and observable perhaps in neutron stars and certainly in the early universe, as well as producing new forms of quark matter, of quark-bound states, pentaquarks perhaps. And there are new experiments that will take the deep and elastic scattering experiments that led to the discovery of QCD to unbelievable new heights. So let me just end with Feynman once summarized all of physics in one sentence. He said, well, some cataclysm, imagine that all scientific knowledge were destroyed. Only one sentence could be passed on to the generation of creatures, the robots, or ChatGPT, or whatever survives nuclear war. What statement would contain the most information in the fewest words with no equations? He said, I believe it's the atomic hypothesis, or fact. It's really beautiful. All things are made of atoms, little particles that move around in perpetual motion, attracting each other when they're a little distance apart, but repelling upon being squeezed together. Okay, with that one sentence, you can do a lot of physics. Well, it's an equal challenge to ask, what have we learned from the Standard Model? And that's impossible to put into one sentence, and it's impossible to do without some kind of jargon. So I think what we've learned is that matter is made out of spin 1/2 fermions. Forces are described by quantum gauge field theory, which exists in 3 phases. There's the Coulomb long-range, unbroken phase, the U1 electromagnetic gauge symmetry. There's the screened or Higgs phase of the weak interactions, based on SU2 gauge theory, and the strong interactions, confined phase, the SU3 gauge group. What have we learned from QCD after 50 years? Well, most importantly, we've learned that it is the theory of the nuclear force. We've learned that in quantum field theory, there exist theories where the dynamics produces all the masses and the couplings from no input, if you want, and everything is calculable. And most importantly, perhaps, we've learned that these gauge theories are dual to string theories. And the real hero in the story, certainly of QCD, but of the whole Standard Model, are non-abelian gauge theories. They, of course, they explain strong interactions. They explain, in fact, the whole Standard Model in its different phases. But they are also dual to string theory. And string theory is a theory of space and time, in fact, of emergent space-time. And that, I think, is the deepest thing we've learned with the most optimistic hopes for the future. So that's the end, but not the end of QCD. I told you I'd run over.
Thank you very much, David. For those who have to run, please feel free to run now because we went a bit over time. But we'll still, if you have questions, I suggest we take a few. And please, yes, unmute yourself. And use.
Thank you for a very nice talk. So since 2003, many exotic hadron states has been discovered. So they're called XYZ states, like the X set at 72 or the pentaquark as you showed. So now we call them as particle Joule version 2. So do you think this would cause another revolution as particle Joule version 1?
I'm not sure I understood the question. You're asking whether the new heavy quark states that are being discovered
Yes.
here at CERN
Yeah.
will cause a revolution?
Yeah.
No, I don't think so. Depends what you mean by a revolution. So people have speculated about quark, hadronic bound states of quarks that aren't just three quarks, like in protons and baryons we know, or quark-antiquark mesons. It's clear that there should be states which are so, hadrons, the nucleon and mesons are like, in some sense, the atoms. They are the bound states of quarks. There might be other bound states. But just like once you have atoms, which are neutral objects, and you bring two atoms together, there's still an attractive force between them, right? Because the atoms are extended charged particles. So there are forces that fall off, like power laws, van der Waals forces, or chemical forces, which give rise to molecular forces, which are much weaker than atomic forces inside the atom, between the electrons and the nuclei. So there certainly are molecular state hadronic states where you have, quark-bound states and other quark-bound states which are bound together. In fact, that happens inside nuclei. Nuclear forces are molecular forces of quarks. They're much weaker than the forces inside the proton. But there could also be states of 4 quarks or 5 quarks which can't be regarded as bound states of color-neutral objects, molecules. And those are quite interesting. Now, in the existing discoveries of these hadronic resonances, it's still somewhat controversial, to say the least, whether some of those states are truly 4 quark states that can't be regarded as molecules or 5 quark states, or not. Now, unfortunately, except for lattice QCD, we really don't have powerful first principle tools for deciding that question theoretically. Lattice gates theorists could answer these questions and predict the spectrum of any number of quark states, but they've been busy doing other things. I think these discoveries will motivate them to do precise calculations and also motivate other theorists to try to perfect other analytic techniques for deciding the theoretical issue. And of course, experimentalists can hopefully figure out ways of distinguishing experimentally these two possibilities. But a revolution in terms of QCD, I doubt it.
Okay, thank you.
Maybe another question? Please.
Hi, thank you for the talk. So I had a small curiosity maybe. So since you presented such a nice and informative picture of the screening and anti-screening in terms of paramagnetism and diamagnetism, I wanted to ask, in terms of, for the case of QCD, when we have large enough flavor, we know that the screening effect, the anti-screening effects gets into a screening effect. So how do you explain it in terms of this pictorial?
If you increase the number of quarks, you're increasing in a vacuum the number of quark-antiquark pairs. That's all screening. So you're increasing the effect of screening. And at some point, which happens to be for QCD 16, you go over 16 flavors of quarks, the screening wins out over the anti-screening. So you haven't changed the gluons. as you increase the number of colors, of course, you increase the number of gluons gets bigger by a factor of n squared, and then you can tolerate more flavors. So the gluons are what is responsible. The gluons, of course, screen as well, but they also anti-screen. And the anti-screen of the gluons is bigger, if you don't have too many flavors of quarks, than the screening of the quarks.
Thank you.
In view of time, I suggest we... maybe a quick question?
Well, maybe very quick, but you alluded about the infrared structure, infrared here. So, for example, you talked about lattice QCD as a way of using QCD to calculate strong interaction at large distances. Now, it's extremely intensive computer-wise and so on. You talked about 10 to the 18 factor. Now, you alluded maybe there's a breakthrough we need in QCD to be able to calculate things like proton elastic scattering. Simple process with QCD. Still not doable right. So this needs a new revolution, doesn't it, in QCD?
Right, but yes. So this is absolutely, which is why there is a renewed interest by somewhat of a renewed interest by some theorists to go back and try to tackle these very hard problems. So problems like diffraction scattering or scattering in general are really hard because you cannot use the lattice Monte Carlo techniques. There are other numerical techniques which are being developed, and hopefully with quantum computers even more so, that one can hope for numerically. But the real challenge is develop analytical tools. And, well, some progress has been made. It's a hard problem. But, you know, we have hundreds of years to solve that problem. This isn't going to go away. The standard models are going to be here forever. We might not be here forever. But if we are, these problems will eventually be solved. In physics, you know, it sometimes takes a long time to solve hard problems. And this is such a rich field. Also, you know, to some extent, experimentalists have neglected these problems as well, because their interest, you know, it used to be central to diffraction scattering, if you want. Now it's peripheral.
Yeah. Now, I have a particular interest in this. I've been looking for glue balls for decades, right, at the ISR and so on. So lattice QCD gives us 3 states, 3 scalars, and they're all mixed up and complicated, and it really needs something, a simpler approach somehow to do this.
Well, but the physics is complicated because those states mix among themselves. They're very broad resonances often. They're really hard. The difference, you know, nuclear physics is hard. Actually, much harder because you don't have the right language to describe it. Here we do, in the end. We have a theory. It's hard to solve some theories. So, you know, typically theorists and experimentalists focus on those aspects of physics where one knows the methods, easy methods, or when knows what the experiment, where precise experimental signals are available. And, but eventually, the problems are there. They will be solved, maybe not in our lifetime.
Thank you. Well, I suggest we thank David again for the beautiful talk.